get started if you can take your seats. Irfan is away today, so I will do the honors. In addition to being a regular physics colloquium, today's talk is also the annual Cobley Distinguished Lecture in Nanoscience, which is a multidisciplinary lectureship that rotates between chemistry, physics, and engineering, and is sponsored by the Berkeley Cobley Energy Nanoscience Institute, headquartered in Campbell Hall. And so we're extremely privileged today to have as a speaker for the Cobley Lecture Professor Philip Kim. Philip is a professor of physics and applied physics at Harvard. He did his undergraduate work at Seoul National University in Korea, and then moved to Harvard for graduate school, where he was a student of Charles Lieber and obtained his PhD in applied physics in 1999. After that, we had the benefit of attracting Philip to Berkeley as a Miller Fellow. And he was here at Berkeley in 1999 to 2001, when he started some of his first pioneering experiments, I think, with thermal measurements on graphene, something that he's been very well known for ever since. I had the honor, actually, of recruiting Philip to Columbia as a faculty member when I was chair of the department there in 2002, probably the most distinguished recruitment I ever did. He stayed at Columbia for 12 years, from 2002 to 2014, and made a number of major discoveries in lower dimensional quantum systems. In 2014, Philip moved back to Harvard, where he's now a professor of physics and applied physics. He's one of the world's best-known condensed matter physicists working on lower dimensional materials. He's won a number of awards, including the Benjamin Franklin Medal. He was elected as a member of the American Academy of Arts and Sciences. He won the Vannevar Bush Faculty Fellowship, and there's a long list which is too long for me to read. So let me introduce Philip.
Thank you very much, Steve. I think that was a very nice introduction. This seems to work. It is my great honor and pleasure to be back to Berkeley. As Steve said, I spent some time here 20-some years ago, and it was a very fun memory. In fact, actually, I came back this semester as a distinguished professor and spent kind of semester here at Sabatra, and already had a kind of great one and a lot of discussions with the old friends and make new friends. So I have sorry to have only one more month that remains to be here, but hopefully that we can make a kind of more interaction. Okay, I'm going to tell you about the story today about this searching for the new quantum materials in general, and especially focus on this stacking Van der Waals layer. And when Mike Romy, one of the hosts of the seminar, just warned me about this the seminar series. It was more this should be interdisciplinary, and also it's part of the physics colloquium, such that the audience I should address is really diverse, and then I should not get involved into too much of the technical detail. And all of these things are really kind of difficult to pass. Also, I think this week we are just around the corner of this the holiday, so I try to make the kind of topics a little bit entertaining as much as possible. Let's see how much I can achieve today. So the quest of the new quantum materials is something that any condensed matter physicist or any material scientist and chemist, in some sense, is something that quite exciting about it. And often that when I talk with my young colleague that just great research postdoc or this young professor who studied the lab, often the questions I got is, all right, tell me how to find the next cool quantum material. And this is how the questions and the reasoning questions always my answer is, well, I don't know. Yeah, tell me that if you find out something, I won't count it, right? But indeed, this is how questions is difficult. But I can just kind of share one interesting thing everybody knows about. I think this the claimed room temperature superconductor LK99 that maybe our summer is kind of quite exciting and interesting. Unfortunately, I think by now there are a lot of this the follow-up experiments and theoretical work that systematically prove that this is not necessarily room temperature superconductor, or not even just conductor at all. But this tells us one interesting story. I think no one that I know that, although when you just read this paper with kind of great interest, they immediately find that, well, the paper is like this and that, and doesn't look like it's professional. But it was very difficult to kind of claim at once that, this is junk, we should not just kind of pay attention. No one say that. Why is that? How come the reason is we know that material discovery, often this new material discovery, including quantum material discovery, often comes with some of the serendipities. Everyone has some of their right. Someday, one day, just kind of bumped with some kind of things we didn't expect, right? So that's why without this follow high-voltage study, it's very difficult just to denounce anything that kind of some of it, at least it forms kind of the scientific discussions and scientific form, right? But of course, that doesn't mean, serendipity doesn't mean that we just can mix up 100 different elements together and cook it up and hope that something comes around. I would say that's probably not the way that we used to do the science, right? So how we can just kind of manage the balance between these two, serendipity versus kind of the educated guess studies or this targeted study. I think that's kind of where that difficult comes in, that answer, that how we can find out these new materials and how we can just kind of develop the intuition. Right. One good example, kind of opposite end of the example is something like this, that if we have the really good controllability about creating materials, often this actually can lead into some of the interesting material system where that sometimes unexpected discovery can appear. And one good example I can just kind of say that here is this, the growth of the two-dimensional semiconductor heterostructures, quantum structures. Usually there are many different ways, including molecular beam effects I'm showing here, the MOCVD molecular, MOCVD method that allows us that one can grow these semiconductor structures almost atomic layer by layer. And this technology has been developed over probably half century or so. And now the kind of way that one can just really stack the material almost atomic layer by layer with all the constituents, so they can increase the control as long as the nature allows you to just kind of stack this material together. One can come up with these atomic layers, almost layer by layer, provide a rather interesting and intriguing functionalities in there, right? And often that once you get into such a good controllabilities and engineering is getting there, that unexpected surprising discovery can happen. Now one example I can just use is that this fractional quantum effect appears in those kind of semiconductor structures. Once you apply a very strong magnetic field, somehow the electrons start kind of to combine with the magnetic field, so-called flux attachment, and coming to the self-organized is a rather complicated but really well quantized and exciting correlates that appears, what we just learned about the so-called fractional quantum effect. And these are kind of good examples that once you have the really good controllability about the materials, and often that it comes around it and unexpected the discovery. All right, the story I'm going to tell you is not about the semiconductor quantum structures, but it's about its graphene and possibly and 2D materials, and which has been around about probably 20 some years for now, right? And as I advertised, to make this story a bit more interesting and following a history, rather than I included all this kind of interesting recent development, I'll just talk about something about the diagram of history and personal anecdote associated with that for most of the time. And toward the end of the talk, I will just kind of finish with some of the recent development that I know a little better. Right. So what you see in the graphene is basically a connection of the material consists only with the carbons that form this hexagonal network. In fact, the graphene has been known for a while, And because part of that is graphene is considered so-called conceptually mother materials of the old graphite carbon. So when you have this graphene stack them together, conceptually you can get the graphite and you roll it up, and you can do a nanotube, you carve it down and roll kind of in this small molecular form, you get a buckle. And conceptually it's mother material, but historically actually it's the other way around. We discovered, of course, graphite has been around for a while, for a long time. There's a lot of seminal work that is done by kind of the giant of the science in this area. For example, David Westerhouse worked on this graphite for 70s, 80s about these experiments. Here that Marvin actually did seminar studies about the theoretical work on the graphite. But then around this middle of the 80s, that group of chemists discovered that this the form of this graphite carbon is a molecular form called the optical C60. Of course, the subset of these people get the Nobel Prize out of the seminar discovery. Around the 90s, and the Sumio Isma actually found that this tubular form of the nanotube, which actually is another interesting period that launched sort of in nanoscience, where the Carbon Institute is also kind of deeply involved here. Right? So what you see here is naturally that a lot of this graphic form has been studied, but in some sense, the graphene, which is conceptually mother form, has not been just kind of discovered yet until this time scale of it around the middle of the 90s, right? Why that experimentally has not been discovered? As I said, that theoretically graphene has been well known, and it was in fact the starting point of the study of any graphic system. Already in the 40s, late 40s, that Philip Waals, a Canadian physicist, took this quantum mechanics and calculated simple band structures of the graphite. And there, then, of course, he decided with a single layer of the graphene as a starting point, and just kind of considering this stacked single layer graphene band structures, you can explain the graphite, the electron structures there. Already the methodology that he used is simply just using single, the kind of simple pipeline model in the nearest neighbor, which often that we can just give away that the incoming example that created students, the solid state physics, tells you already many things, right? For example, that if you have the real space of this hexagon graphene, set it in the cell, there are two carbon atoms in there, and then anyway, we say this this triangular shape, then momentum space of the description of the block electron to form the band structure is hexagons, and there where the interesting corner point is interesting. Importantly, that when you just can put the two carbon atom per lattice and do the band calculation, Waals found that indeed energy dispersions near this charging neutrality of the graphene is a kind of interesting separation of density state with the dispersion is linearly dispersing. Already, if you just kind of look at the band structures, indeed that near this the suppressing point of the density state of charging neutrality graphene, dispersion relation is strictly kind of linear, or like the following. This charge list, the mass list particle dispersions that has been known in behind physics, right? So already this kind of the quite a long time, the graphene, if you just look at the electron band structures, it looks quite interesting. But quickly you see that this linear dispersion is not just analogous, and throughout this 80s, people start to realize indeed this description, linear dispersion, is tied with some interesting physics that coming from higher energies, right? This is paper by the Vincenzo, when he was a student of Jean Miller. They actually just kind of expand the pipeline model near this charging neutral point of the point now. They just express the equation is kind of followed more right in the part of the equation or wide equations that actually have the different depths. Simply, it's kind of spin of description is natural because I have the two carbon atoms in the cell. Right? Where this actually, around the 80s, can be discovered by even the high energy physicists like this Gordon Incidentals, because actually follow the independent work to write down the graphene band structures and remain as a high energy languages, published in the PRA in the first page. So which is kind of quite rare to see that a condensed matter system appears in that band. This is kind of interesting. even the Duncan Harding took the graphene model around this times 88, 87, and formed this the famous the Harding model based on the very similar description started out. Right? Of course, that when the nanotube comes around, we know that nanotube band structure is nothing but rolling up the graphene band structures, right? So very similar structures that can be just be transmitted to the graphene band structures. Here is a kind of work from the Berkeley, that collaboration between the Donghai Lee and the Stephen Louis, beautifully show that indeed, even for the nanotube, the band structures of the electron move inside the nanotube, especially if the nanotube is over the chiral nanotube, the armature nanotube. Precisely those kind of direct description type of the band structures can be applicable for the graphic system, the graphene as well as the nanotube. Right. So around the 90s, what happened? I just graduated, and then I came to the Berkeley to study my postdoc work. I worked at core mapping. I knew that this is a young old here, young old the poets here. The first meeting I asked him, of course, okay, so I'm here, what do you want to work on, right? And interesting enough, the Paul said, all right, so, oh yeah, have you heard about graphene? Of course, I work on the nanotube, so I know about the graphene. And he said, oh, well, why don't you actually make the graphene? And that's the story about it, right? And there's a reason that actually that he suggests that why the study graphene can be kind of interesting. And that required kind of one piece of the physics, which probably we all know about, that I can remind you. It's actually related with kind of peculiar property of the spin half object. Right. So let's think about the electron, which is spin half object. Of course, the electron is not a ball, but if I just assume that it's a ball and we can spinning around the ball, can create this magnetization. And of course, quantum mechanically, the describing of this magnetization is related to spin, right? But as a magnetization can be a three-dimensional vector, it can be kind of pointing any directions, and naturally, they can ask how many components I need to describe this magnetization. Answer is always a three-dimensional vector, then maybe I need a three component. We all know that answer is wrong, because it's a spin half can be explained that everything is a two component. Even the x direction of the spin direction, I should be able to explain by the superposition of up and down spin, right? And this is a little bit weird because although this is a three-dimensional vector, I need only two components to explain it because it's in terms of the spin SU2 type of this vector space arguments, right? And these two components, this gives a kind of rather weird property of the spin wave function. In other words, basically, if I just rotate the spin, so 360 degrees, this wave function does not come back its own, but it comes with the sign changes, right? Which means that only when you just turn around the electron spin 710 degrees, it comes back to its own, right? So one turn is basically kind of corresponding half turn, right? What it comes from is basically it's related over the very phase arguments in the model magnitude. So you need to explain that spin half is kind of interesting things. When it comes around, we need to count twice to compare its own. So something like topologically interesting in a sense it follows the kind of maybe split arguments. I have to come around maybe straight once, then it comes back out in opposite direction. I only come and rotate twice, then it's come back its own original position, right? So already we start to see that spin half object is a kind of rather minimal quantum mechanical object, which can be quite substantial, and it can be called this topological in a sense, the reliability very phase argument. Precisely this type of argument was taken by some of the physicists in the late 70s. Right? It was actually first that clearly spells out by the June Ando's papers in 1998. And this paper is published in the Journal of the Physical Society of Japan. Let's just take this the rough description of the electrons in graphene, the nanotube, right, and show that, since Hamiltonians only consist of the spin of a couple, or actually this case is not the real spin or pseudo spin, so the momentum connection term. Therefore, when the momentum is turning around, your pseudo spin, which is a spin half object, is turning around, which means the wave function will basically acquire about those kind of unusual value phase coming from spin half object. Right. So that's basically what this June Ando's kind of this paper is indicating. somehow around that time, that the team that led by Paul McQueen and Steve Louis just can pick up that idea and apply to the transport into the nanotube. It was actually a real paper I found that Paul McQueen is first author, and the Steve Louis is the last author. Of course, the last author is a professor. But it actually makes sense because this is not the experimental paper, but collect all the experimental paper and reinterpret in terms of these static phase arguments. And indeed showing that because of these static phase arguments, that you have the really long linear path is expected for the ventilating nanotube, where you have to consider this, the pseudo-spin directions and static phase associated. Right. And that's the reason that why Paul asked me that when I arrived around this time, right? Hey, why don't you actually make a graphene where you can test this visibility out, right? Just starting, you propose out what you can do. All right, your boss is asking to do something. I just kind of, all right, so let me just try to do that. The first thing you have to do is go to the sound room that I wrote this, the lab note, and just wrote down the graphene lab note, right? And this is my lab note from the Berkeley. And I actually try to make a graphene. Basically, this place. I think that I was kind of walking into somewhere that back then this building is called the Lacon. Somewhere in the first floor that my lab was there. And I was reasonably successful. So the way that we did it is that we just bought the graphite powders and just sonicate it out and spread it over to the substrate. And you see that I made the devices out of it, right? Well, this is a device fab. And then we just measure it and just get this some conductance as a function of temperatures and all kind of things that, I worked it out okay. We get some few layer of the graphite, but you know that I was at graphite powder, it's a lot of disorder, not much interesting things going on, and I complained before, yeah, you gave me the shade product, it doesn't go well. And company enough that I just escaped from the nanotube and measured thermal transport, so I got saved, right? But then, after all this, the interesting failure, when I started my lab, Steve Kahn just recruited me to Columbia and started out my lab. I thought kind of, well, you know, sometimes we can just do something easy, but sometimes I want to do something kind of challenging. So I thought kind of retry out this the graphite project or graphene project, right? So the one way that we can think about getting the graphite or graphene is just look at the pencil, and pencil lead made of a bunch of the graphite or graphene, right? So when you just have grab the pencil and write on the paper, you'll probably clip it off at some of the thin graphite sheets, maybe in graphene, right? So that's our idea that we can think about is, well, we can just do the very similar things, except that maybe you can just kind of make this pencil a little more controllable, right? So what about that we just kind of make so-called nano-pencil? And there, I had my first student, Yang Woo-jang, who happened to be sitting there. I don't know why he's there. Yang Woo is also visiting from Fudan University now. I have to the same time. Back then, Yang Woo was young like this. And Yang Woo was kind of foolish enough that to believe that my kind of crazy idea. And he made this really nano-pencil, carve out the graphite crystals, and just make this little blocks. And attach to the this AFM candle. I don't know how you did it. But then just kind of scratch onto this surface and just try to get this more crystallized. Right. So that's kind of how we try it out. Sounds like a crazy idea. But Yang Woo was dexterous enough, smart enough also, and they made it work. So as you see in this, that you just kind of create some crystal. I think it's not a single layer, but some of crystal is very thin, something like a few nanometer thick, right? And this crystal is high quality HPG, so when you do the transport measurement, there's independence, there's magnetic resistance oscillation. So it got kind of quite fun, and we got really excited about it, right? Because we started out the bulk crystals, now we get a few nanometer. I think probably about 10 layers of that. We get about 7 of those magnitude down. I have just we need only 1 order magnitude down to get to the single layer. This is good, right? Well, you probably know what happens there, right? So, by the way, if you look at this time, we submitted this paper August 2004. That was kind of interesting somewhere. Around that time, they heard the rumor that there are crazy people, it's actually crazy like us, that are just doing very similar experiments. And kind of quickly comes out these guys that the guy and also in the Manchester University published it around that kind of few months after us, this paper, and completely screwed our project. Okay, that's basically the day that I remember that reading this paper. Oh gosh, it's completely screwed. What happens to my career? Because that's why I was just the second part is, of course, what kind of weird curious, how they get this single layer on the graphene? Clear that they experiment is very similar to us, except that they went to the really literal single layer. Right? Everybody knows that now. I've been using stress tape. But remember that when we spent about 2 years to look at this, and then just read the paper carefully, and I found that, oh gosh, they use a stress tape to get this one. That was really hard to go. Of course, a few years later, then we got another blow. So you actually got another prize. But I think the other part that I remember back then, just reading this paper and really found that they use a stress tape, get this thin layer. I just realized that this story is not just new to me. Because when Paul asked me to kind of get the single layer graphene, I read a couple of different papers, how people attack this problem previously. Right? There comes basically this interesting person, Bob Fick. Already in his 60s and 70s, he went through the studying Cambridge University Cambridge, and then he moved to Simon Fraser University, and he did actually a lot of interesting studies. He just studied getting very thin crystal out of the 2D system. Right? Here is a kind of one example already in the 62 that look at this, if you have only disulfide, which is another 2D semiconductor, you got a very big crystal something. Right? And I remember that actually I'm reading this together paper we had in the 70s, 1970s, he published a solo paper, experimental paper. In this paper, basically he showed that very thin nylon diselenide, by the way, this is a superconductor, well-known layered material superconductor. He demonstrated that he get this very thin layer out of it and measure the transport as the layer becomes thinner and thinner. TC was dropping down because of fluctuation effect appears in the lower end. Right? And if you just read this paper, which I read, was mentioned there, the thin crystal is obtained by the sticking substrate and repeatedly peel it off. Precisely that's a method what kind of Manchester folks use, right? So I felt like, oh gosh, I left my key in the porch when I started out. So that was my theory. But anyway, so this actually gives some lessons, like read carefully about the literature. Right. So in a sense, graphene research has been kind of launched in kind of rather interesting in silly way in some sense, but it actually brought us a lot of exciting things kind of almost immediately. Right? Next year, that collaboration, well not collaboration, competition between Manchester and Algo, will show that high enough quality of this two-dimensional system on the direct dispersion relation, you get this big quantum effect where sequences are rather intriguing. The sequence is going like 2, 6, and 14, and you can quickly say this is not nothing but just a generalization of the 4 times of this half integer. In fact, this the very existence of half integer is precisely related very base, meaning that turning around the once of the orbits is equivalent of the half count. That's basically this kind of meaning of the half integer, precisely showing the importance of this very phase associated system is inserted. Of course, those kind of the very phase associated with the linear dispersion, once you apply the magnetic field, the lambda levels appears, but the lambda level separation is very different, especially the first lambda level separation between 0 lambda level, first one is a big because of this linear dispersion relation, which means that with the decent magnetic field, meaning there is a 30 Tesla or 40 Tesla, the gap becomes kind of several thousand Kelvin, which means that the quantum effect appears in the room temperature. Right. So not the superconductivity, but that is working with the quantum effect in the room temperature. But also this is kind of interesting moments that launching this new kind of avenues about getting the materials. So graphene is in a sense the first of the kind that one can get the atomically material by a simple method, by just kind of extracting or cleaning off from most crystal. But nature provides us a lot of different so-called layered materials, where between the layer it is a weak van der Waals force kind of holding it together. Right. Soon after, that community realized that there are other materials that with this very similar way that we can extract the graphene, one can get it. For example, the hexagonal boron nitride, which is the same as a graphene, but except that two carbon atom is replaced by the boron and nitrogen, which is insulated, can be extracted as a single layer form, but then something like a traditional conventional as a mentioned a few examples previously, came along very similar category. Not to mention about some of the other systems, including high temperature superconductor and organic and inorganic systems. What is interesting part is all these materials actually comes from very different flavor in terms of electronic properties and other properties. Some of the material is semiconducting, some of them is metal, some of them can even be superconducting or topological insulator. Many of them has common things though, because this weak van der Waals interaction, principally we can extract these materials and down to one monatomic layer where things are extremely confined such that you can just study about their two-dimensional things, right? But on the top of that, because it's a weak van der Waals interaction, in principle you can just restack them together, right? Then you can just kind of choose the different materials that you can stack it, and in principle you can make this kind of positive three-dimensional system with different functionalities in there. And this type of the probability, the possibility, has been immediately kind of discussed among scientists working in this field. And soon, that this is not just PowerPoint kind of generation, those kind of examples can be made. Here's a good example that the collaboration I had at Columbia University, especially with Jim Hunt's group. The method is kind of working something like this. You clean down the crystal. Okay, like this, you clean down the graphene crystal on the surface. And using the scotch tape, you can pick it up. Not the scotch tape, but sticky tape, you can pick it up or stamp. But then you can just do this in the repeated way, such that you can make this van der Waals stacks consist of all different layers of materials. In this particular example, it is graphene, and you start with boron nitride, pick up the graphene and another boron nitride. So you can see that graphene is a sandwich between this boron nitride layer. But if you just read right, and if you just make it cut through the sample, look at this interface, and you see this interface is extremely clean. Right? And you see that this type of the TM images are very much mimicking. That's what I mentioned in the beginning about how much we can have the controllabilities getting the semiconductor heterostructures. Except that this is not necessarily semiconductor, but here the insulator and encapsulating the graphene between. Right? This technique has been evolved in such a way not only you can stack them together, you can just apply all this microfabrication technique such that you can just clean it out or you can just etch onto the part of the crystal, make the contact on the side such that you can make this good contact onto the encapsulation side with a very different way. And graphene, which is just consists of single carbon atom, has a less defect once you just grow that into the really improving condition. Encapsulated boron nitride, which is in the crystal, immediately boost the quality of the sample such that electron can scatter only about 10 or 100 microns that going through to meet these defects or the central edges to scatter. Such a high quality and large mobility immediately allows us to study interesting quantum physics. For example, if you apply the magnetic field in the graphene, now with such a high quality graphene with the visual magnetic field, something like 10 or 20 Tesla, which can be applicable in the lab. This result is from, I think, the 40 group. Beautifully show that graphene also developed this integer, not only integer quantum effect, you see the series of this fractional quantum effect appears. It's more of this, the fractions, and especially so-called even denominator quantum states, which is one of the most common coordinate systems regularly appear in the graphene, such that one can study interesting physics of it. Right? So what I'm saying here is now we start kind of catch up using the graphene that one can and get this kind of high quality. You can study about the interesting physics of it. So let me just share one interesting physics that we can just do. Which in this case that as long as you have a high quality electronic system. We say applying the magnetic field and create the quantum Hall effect. One thing nice about the quantum Hall effect is basically the electron is only moving through the edge states. So let's imagine that I have this stack of the graphene encapsulated in boron line, right? But then I put this the graphite on the top and bottom, which actually act like the gate. But we can just pattern this gate into the various sections. By the way, this technique is nothing new. This technique has been borrowed from the semiconductor heterostructures, where the one can make these quantum devices, right? So what you can do is you then apply the magnetic field to the various fabrication steps. And once you created this type of device, you can see that the segments there. Applying the magnetic field, electron is flowing through the edge of the sample, but in this particular case, edge can be also created by the segment in the gate, right? So the experiment can be just kind of done in the following way. The electron is flowing through these edges, right? But some of the electron is going through this bed of the world that what we call this quantum point contact, that controlled by the being the central gate voltages, and getting into this chamber. But then it's going out through this chamber and coming out, and we can just measure it. So this is, in a sense, that what you can say is a fabricate interference. In a sense that if I just send a photon through the waveguide, and it's a kind of beam splitter, two beam splitter, then photon will just kind of bounce back and forth and coming out. You can see the photon will just interfere into this fabricate cavity and work at this, the intensity of the photon coming out from this cavity start oscillating as we change the pathway. Right? Very similar experiment, we can just do the electron, sending the electron through this pathway, and the electron phase can be modulated by applying the magnetic field, which can modulate this out of one phase getting there. Right? So using this method, basically, we can just, as if we can create the interference of photon, we can just do that for the electron following through this path. And indeed, when you just do that, and simply measuring the conductance of electron coming out through this series of the quantum point contact, which actually Cartesian electron wave function, you see that there's a beautiful oscillation appears, and that's basically as you change this further gate, which actually changes the area of this cavity, controlling the fabricate oscillation or out of one oscillation period, we get those kind of the interferences getting there. Right. This is a good example that indeed having these high quality samples with the fabrication tied there, you can study kind of about this electron interference phenomena. In fact, this can be pushed further, especially that if it is not an electron, but if it is really a fractional quantum states, where that you can get this not only electron, but those kind of composite fermion, which actually because particle comes in anion, where the grading scheme or the this exchanges statistics different, we can attack those kinds of things again, those kind of interferometry, and we start to see that indeed there is a kind of tantalizing evidence. It's not simply the interference, but there is the phase slips and there's a frequency doubling, which are all kind of related with this electron that transport through the whole electron of course particles transforming through the edge state and impact each other, giving this kind of interest phenomena. So this good example is something that I can give you that once you have a simply high quality sample by encapsulation, one can study about the intrinsic physics and potentially using this as a device skill. But nice thing about the system is you don't have to just work on single layer, right? For example, you can just stack them together to multiple layers, right? Here comes that the graphene, another graphene, just can put them together with some of the separation layer. You can see that it's a thin layer separating that boron nitride. If you use the reasonable thicknesses, two layers are well separated, there is not much tunneling. You may say that may not be kind of exciting things going on, but it's not true because electron in the top and bottom layers stay detected by the plural detection, which is long range, and they can produce something interesting phenomena. We'll discuss that example later. Or you can just kind of go for completely different schemes. Instead of graphene, then I can just use the other layer. Here, that example, the tungsten diselenide and molybdenum diselenide, N-type and P-type semiconductor, we can put them together. You can say view that this is a world thinnest the PN diode, but at the same time, because of this strong confinement of cadmium 2D, this can actually also view or behave the quite interesting behaviors there. Well, you can just kind of go for the problem, right? Right, so this is one of the hero devices we recently made, or my students made, and they are recently made. It's kind of something like this. It's boron nitride, there is a graphite gate and boron nitride, and there is a twisted bilayer which I'm going to explain, but there's a two-layer of these layers stuck together, boron nitride, these layers, and boron nitride, and count this. And then if you count, it's about 9 or 10 different the layers stuck together. I don't know how many people, but anyway, as a kind of reasonably high yield, I should say high yield, but reasonable success rate, you could make the device out of it and you can study about this interesting problem. Right? So these examples show that indeed we can build up rather more complicated functional device with various different choices. So what can do? Well, again, one can think about some technological application, but as a physicist, we can think about can I actually study about interest physics. Of course, there are some of the physics we can study, and I will just share the two examples out of it, which is related with condensation of boson integral field, especially composite boson integral field. Like the superconductor, where the two electrons form the Cooper pairs that make the condensation. Cooper pairs boson integral field made up of two particles, right? Superfluid helium, which actually is again condensation phenomena, consists of the helium-4, which is collections of all the ferromagnetic helium, but they form this composite boson, which actually is size. Right? We know that our colleague in the AMO communities, if you're dealing with the composite boson, by controlling the constituted ferromagnetic interactions, you can control size of the composite boson, especially in connections with the interbosonic separation with the bosonic size. You can come up with this condensation with a different phases. For example, if the bosons are well separated and tightly bound, of course we can get more like boson-cell condensation. But if the boson is loosely coupled and they start kind of interact rather strongly, it's more like this loosely coupled cases, you can get so-called the BCS type of condensation. And AMO physicists can control those kind of the two different phenomena, the crossover, by simply controlling the size of the boson relative to their density, right? Anything is similar thing to solid state. Well, there is a few examples that one can just come around, but one example that quite kind of studied for the proposed many years is using the exciton as a decomposed boson. When you shine the light on semiconductor, we get excitation of the electron from field valence band to the conduction band, and remaining is a hole within the inside the electron can form the bound state of what we call the exciton. And of course, exciton has a usually finite lifetime. But imagine that somehow if you make the exciton is low enough, almost infinitely low enough, that you can envision they can form the phase diagram. Indeed, the theorists, assuming that we can long leave exciton, they come up with this kind of phase diagram of exciton, pretty much following through the what is expected for any kind of composite boson. Here the important part is an exciton density can be controlled by the various means, and the temperature, you get this condensation or the non-condensation to condensation, which is actually controlled by the exciton density. Can you actually realize this type of the things there? And again, semiconductor heterostructure, this has been attempted. And the way that they come up with a really ingenious idea, you started with the semiconductor quantum well and create this intralayer exciton, but once you bias this the quantum well, and you can quickly dissociate this exciton into the electron and hole as a majority carriers living in the different layer, but they can stay bound into the form the exciton called the interlayer exciton. But since electrons and holes are living in the different layer, they can be long-lived. And indeed, using this one, and this is the Newton group's work, beautifully show that if you create this interlayer exciton, pumping of the interlayer exciton, they start to see that interlayer exciton start kind of soup of the interlayer exciton start kind of develop self-organized the coherence in there, which is the very first step of this seeing this condensation. Why this is really tantalizing the development here, this has been hard. Part of the reason is an exciton it is still kind of short lived because quantum array in this semiconductor quantum matter is not bounding this electron strong enough and kind of leaking out the electron, make the recombination. And also, the strong direct constant of the semiconductor strains exciton to make the binding in the small. Right? So this experiment can be run in the very low temperature. Of course, there comes that 2D system is kind of one of the rescue. Because by just choosing the right semiconductor, something like the tungsten disonated or disonated in this way, they can immediately form so-called type 2 elements, which means once you excite the system by the light or inject the electron hole to the system, they readily form the internal exciton, which actually was studied quite well by that one group here, right? And moreover, this internal exciton can be quite a long-lived. And also, when we conform these device structures, which actually I showed you in the few slides back, you can control the internal exciton energies by applying the electric field. And also, same way, the gate voltage can control this lifetime. Moreover, the lifetime is fairly long, about even half microsecond, or even longer lifetime can be achieved. And moreover, you can inject the electron hole, but not only the light excitation, but inject by electron hole by applying device voltage. So all of this level kind of give us the hope that there's a way that we can create this intellect in and indeed, by just kind of using the device structures, especially using this top and bottom gates that we can install, we can control the exciton's energy as well. Right? Which means you can not only create the exciton by shining the light or electron injection, usually it's a hard electron or hard force. Right? You can cool them down and combine that, collect this exciton into the trap that you can create. I recently we create kind of those exciton traps using this carbon matching gate voltage applied to control the electric field. And those kind of traps, we start to see that indeed we can collect these excitons in a high enough density. And controlling those exciton density and study about the exciton density as a function of temperature, we start to see that when the excitons start to dissociate and give us a light, we start kind of draw as part of this exciton phase diagram as a function of density and the temperature. Okay, this is rather indirect at this point, and there is quite a recent measurement done in Fairmont's book by the transport, just mapping out this, the phases. But that is to give us the way that just having this type of 2D materials and the structures, we can start to study about this composite bosons, the condensation. Now, one thing that you can see that here is that many of these experiments, basically exciton is not the ground state, and you have to struggle to basically do this condensation. And that's kind of fundamental struggle that we have. But you may ask that, what if somehow we make this exciton in the ground state? Indeed, those kind of experiments can be done. Not using semiconductor structure, not using the semiconductor energy gap, but using the Landau gap by applying the magnetic field. Here's an example that we can apply that magnetic field into the quantum realm, that we can populate the electron, and apply the magnetic field that we can form this Landau levels in each of the well. Right? Well, assume that magnetic field is such that none of this Landau level is completely here. But assume that we just kind of control that also the number of the electron in the top and bottom layer such that although these are the partially filled Landau level for each of the layers, but as a projection, I still have the fully filled Landau level, which means that if I just look at this Landau level, the projected, we'll just kind of make a full Landau level where I expect the quantum effect. However, of course, there's some separation, it's only the projection you have, so it cannot be just make a kind of full quantum effect. But nevertheless, in those kind of limits, we can see the interesting phenomena. If I have the electron on the top layer, bottom layer, electron will try to avoid this electron on the top layer by pull-off intention, to bring the holes behind, right? And vice versa, right? So when you just look at those kind of situations, although each of these layers are partially filled, you just kind of build up these small arrows to connect the electron hole in top and bottom layer. This is kind of dipole arrays that is kind of build up the all these kind of lattice. Right, as a full quantum effect. If you just go through this all the mathematics, right? but basically mathematical, the expression of those kind of situations is precisely mathematical expression we expect see in the axial condensation states. Right? In that regard, then we call this is so-called magneto extant condensation states. And precisely experimental observable here, you may expect to see that the condensated extant behavior in the system, right? Which means extons that flow like the superfluid, right? So that can be quite cool. I would say that this experiment was precisely done around 20 years ago. Series of the experiments done by the Jim Eisenstein and some of the other the colleagues beautifully demonstrate that case. One beautiful experimental demonstration can be done in further way. If you just connect this to bilayer in this magnetic condensation state, connect this electrode onto the kind of top to the bottom, right? And send the current through the top layer from here and return this the current from bottom layer, right? Imagine that this system is now consists of the exciton and condensated, and I will just call this top layer the whole layer, bottom layer is electron layer. The current is flowing like this, electron and hole is flowing like this, and then current is flowing like this, which means the electron is flowing like that, right? Because the electron holes is bound to exciton, in that geometry, basically, sending the current in this way is a way that I can move the exciton from one side to the other side, right? But remember that if the exciton is condensated, it's an exciton superfluidic state, which means that there is no dissipation that the exciton is moving from here to there. Right? So this is exciting cases that each of the layer is that narrow. It doesn't conduct electricity well, and there are a lot of dissipation. But once you just connect them in this way and send the current in counter flow geometry, you get more like the zero resistance states in counter flow geometry, and that's precisely this experiment that you showed. Right? So now you start to see that by tricks, right? As a non-imaginative person like me, right? So what is the next experiment you want to do? I give you already the trend, right? So both experiments, we have this nice high quality graphene, crank up the magnetic field with the reflection of quantum effect. Second example, I see that the quantum well guys, the semiconductor quantum well guys, maybe quantum well do the exciton condensation. I just copy that for just the PFDC. So what do you do? Well, we copy the same experiments, simply just replace the quantum well with the graphene, and just to do the same experiments. Right? What is the point of the doing this experiment? The one important point is that electron is now very strongly confined to graphene. We can put them together very close by, right? So we can actually increase the exciton binding energy quite high. That allows us that we can just do these experiments not in the tens of millikelvin, but 10 kelvin. Almost 2 of those, 3 of those will be larger. Which allows us now, we can carefully mapping out the phase diagram of the disk condensation. And that's kind of what you can see. So we just kind of put this counter flow geometry, and I can plot it out how the resistance changes as a function of temperature and magnetic field. And this magnetic field is basically controlling the magnetic exciton densities, right? What you see is that this red, dark blue, is basically zero resistance, zero counter flow resistance, which is condensation, right? As you go to the temperature, it becomes non-condensation. You see that this is nice phase boundary, you can see, which is nothing but we are seeing that how the exciton condensation is changing as a function of temperature with the magnetic field. Particularly that if I just make the cross-cut the constant magnetic field, is basically a high magnetic field is cut through there. Temperature, finite temperature at the finite counter flow resistance that turn into the zero resistance at the low temperature. Well, look at the flow. If I just hold this is not counter flow resistance, but just resistance. What do they look like? This will look like superconducting conditions. Indeed, for study about this region is basically related with indeed the dose and the transition can be viewed as indeed the BCS like the transition, while that as you go to the lower magnetic field, where the exciton is well separated, transition turn into the DC type of transition with nice crossover you can see indeed. Right. So those kind of phase diagram, what the audience actually expected, can be just kind of experimental prove in this type of phase geometry. Right. So I don't want to hold you too long, but of course, that when it comes with this two-dimensional system, especially in past for a few years, you cannot just go around without talking about sort of the twisted layer or twist orbits. So the idea of the twist orbits is again coming from this van der Waals layer system. Because this van der Waals layer system, when you stack them together, it can be stacked with any arbitrary angle or some twisting angle. Right? Quickly you can see that when you just put these two layers together, because of this quasi-periodicity appearing from this twisting, there is so-called the water periodicity appears, which actually allows us to engineer the further the band structures of any of the 2D systems. Right? Not to mention of the graphene, when you just put this some twist angle, those kind of water patterns give you somewhat different type of the quasi-periodicity. Indeed, utilizing this type of quasi-periodicity, few years ago, a group led by Pablo Javier and MIT, discovered something really shocking and sensational. They just put the graphene at so-called magic angle 1.1 degree, and what they see that is graphene coming to the first insulator, or the so-called correlated insulator. Opening that correlated insulator, they start to see superconductivity. That was really completely unexpected, except that there is a kind of paper 10 years ago that flat dynamite forms. But this is again another interesting way that serendipity is sometimes kind of interesting. No one expected what case. Few people expected that can happen. No one actually, including myself, didn't believe that this can happen. Part of the reason is when you just kind of form this layer, well, you get this all these strings and you have the reconstructions. How come that this is a simple theory that based on the tight binding model or the continuum theory that without consideration of this the relaxation can be done kind of this surprise reason? Well, there are a few people who really kind of pursue this one with the full heart and kind of see those kind of the exciting things. Of course, once this type of seminar discovery is made, then many people kind of repeat those kind of experiments and quickly expand them. For example, not only single layer, if you go to the multiple layers, 3 layer, 4 layer, now 5 or 6 layers, it can be not only single layer graphene, bi-layer graphene, you get this superconductivities and magnetism. A lot of interesting things kind of quickly pops up. Not only that we can just look at those kind of properties, there's now that people are looking for that whether this property is tied with the new physics. So often this kind of requires a nuclear tool development. For example, that nuclear is a superconductivity. One of the important questions here is what is the order superconducting order parameter? It is really conventional. There are, we can just borrow the techniques that people develop in the Q-plate, for example, make the corner junctions and just try to look at this superconducting order parameter symmetries out of it. Or you can just kind of shine these RF lights out of the wind and just try to measure this kinetic inductance to the superconductors and try to kind of use that as a the sum of the probe to look at this unusual superconductivity. And in the field it becomes quite exciting because this new discovery of quantum materials also enable many different tools that either developed and undeveloped or newly developed can be applicable in this system. Finally, I want to say that also you can just kind of branch off this two-dimensional physics, not only just the simple system, but you can actually combine this with rather strongly correlated systems like the Q-plate. Many of the Q-plate also comes with those kind of layered structures. Often that this kind of layered structures can be cleaned down to down to mono layers. The system. There's in fact there's a beautiful experiment demonstrated a few years ago by the Yangon Jiangsu at the Fudan University. Down to mono layer of the visco, you just kind of contain this kind of the exciting physics there, right? If you don't do this type of physics, what you can do? Okay, again, we can just kind of copy the already existing system. For example, you can now form these twisted junctions of the visco, especially at the 45 degrees twisted junctions, where the interfacial superconductivity start to develop onto the primary symmetry broken 2 minimums, which actually can be utilized as a building of the Josephson diode. Josephson junction with the diode effect even appears in the fairly high temperature, something like 50 Kelvin. Right. And these are kind of another example that you can also branch out to the physics into the interesting direction once you combine into the new materials. It's not only the physics, however. So this is the result coming from the Corvinus group recently. But one can also build up the heterostructures and create this kind of lattice interface, and you can just induce some of the different chemistry. For example, you can intercalate those kinds of different interfaces with different type of ions. And it turns out, by controlling these different type of heterostructures, and you can control different type of chemistry that realize into the completely different material platform, you can induce the interesting chemistries in there. So all of these things that bring me to the kind of final, the concluding remark. So I think that I remember that I came here roughly about 5 years ago, that I gave some colloquiums and some seminars there, and was kind of clearly answering this type of this diagram. Right? These diagrams show that, hey, there's a kind of different 2D materials, right? And this graph can be kind of zero gap semiconductor, insulator, semiconductor, superconductors, and things. Repeating same things and just can show that, hey, we can get this many different interfaces with various different combinations. Right? And I argue that, all right, our phase space is really large and you can explore a lot of interesting and exciting things. Right? Well, that was 5 years ago. What happens in the past 5 years? A lot of things studied, right? But then we missed out one important part, and we now find out there's yet another degree of freedom, which is this twist angle. Now, unlike this two other degree of freedom, which can be infinite but it's uncountable, twist angle is basically uncountable, infinite kind of choices. And that's somehow the make this field really exciting. Now that we have a lot of the very wide phase space we can explore to get up to this new quantum materials and quantum system, where we can study about interesting physics and chemistry and material science in there. With that, let me just thank my group, so it allows me to give this talk.
Thanks, Philip, for a fascinating talk. We have time for a few questions.
So, do you think that 2D materials can make Josephson junctions that will have lower coherence times and dimensional superconductors make better qubits or quantum computers?
The long coherence time, the low coherence time. Right. So I think that's kind of one of the goals. I hope we do. Already people claim that the using boron nitride instead of having oxide, you may actually substantially enhance that coherence time of the conventional qubits. Because a lot of conventional probably don't know kind of better, but a lot of conventional qubits, basically there is the switches into the oxide or just kind of the degrade those coherence time. So idea is basically when you have the boron nitride, which actually is a single crystal, there is no length bond, you may suppress those kind of the distribution of the switches. And indeed, some of this, the people just demonstrate using the boron nitride as the insulator, that there is a report that quite a time that substantially enhanced. Furthermore, I think that ultimately, if you just can somehow realize this topological superconductivity based on this combination of 2D materials, where there is some of the reciprocities, I hope that those kind of topological superconductivity you can even enhance the requirements for the formation. But that's remaining to be proven. I thought we are asking questions.
I just did.
Okay.
Question back.
The BEC crossover.
Yeah.
Is there some reason why the BEC state resistance you dropped a lot? Like why do you get face like much stronger?
Yeah, so that's a very good question. I think if you just look at the detail, in fact, so this BEC analogy is a limit of the analogies, and the detail is somewhat different from just the AMO type of BEC crossover. part of the detail, the structure is different, especially the EC limit. EC limits, it can be back to so-called the XY, the magnet type of thing. And then there that this the crossover is happening by creating of this defect on the condensation. And usually this defect is what people call this narrow and narrow pairs in the XY or anisotropic XY model. And it requires a bit of the activation energies. So it look like kind of gradual changes, but if you just look at the RMS plot, you can get that there is some characteristic, the activation energies, which is related with the defect formations in the condensations.
First of all, I need to just the presentation. I have a question regarding the future of the fundamental heterostructures. Do you believe that some more breakthroughs and they could be discovered in this system or some more unexpected physical phenomena?
Okay, that's a very good question. I will just kind of go back to my first slide. This future is of course very difficult to predict, and there is no kind of known recipe there, right? But I can try to do the educated guess in some sense. There are always kind of some certainties on a lot of materials, and also they working on these materials and the new materials. There are always some trend, right? So sometimes materials becomes popular, but then there is kind of going over the next systems. I think the 2D materials and 3D there is yet some difference, though, is related with the last slide I did. Somehow there is a lot of the white spaces available, right? And including different choice of the material, including different way of stacking. So although we are using kind of similar kind of material approaches, system we can create is quite diverse. And that the physics get involved into this thing, getting into the really single particle physics, so it can truly correlate physics. So all kind of the different type of things is available. I surely believe that simply the space argument, there is a kind of good chance that some of this unusual discovery can happen. Right? So what it is and where to find is very difficult to predict. And in some sense, there even just a theory guide is necessary to kind of really narrow down our search because space is so wide. But I think that if I just bet, I'm sure that there will be more of the exciting and interesting discovery will be made in this area.
Thank you.
Any other questions? Okay, before we close, since this was the Copley Prize lecture, I have the honor of presenting Philip with our plaque.
I didn't expect that, actually.
He also got money, but that was direct deposit.
Okay. It was a great honor. Thanks.